Okay, I'm short here, so let me get that at the right level. I'd like to thank the organizers of this conference for including me in a very stimulating meeting. And I'd also like to thank Professor Wagner for providing a nice lead-in to my talk. Climate is warming. I don't think there's any doubt about that. It's going to continue to warm for the remainder of this century and well beyond, and that is going to have some significant impacts on water resources. Now, while it's not possible to accurately predict the precise nature of water resource impacts at the local or regional level, we're not totally in the dark. There are some types of changes that we can foresee with fairly high confidence. And I think that it's useful to begin planning for those types of changes that we can foresee and to, at the same time, build our capacity to cope with and be resilient to the remaining uncertainties. Okay, good. So let's look at how the hydrologic cycle changes with warming. Warming intensifies the hydrologic cycle. As the surface temperature of the Earth increases, that's going to do a couple of things. First, there will be more evaporation. As Professor Curry noted, over the ocean there'll be a lot more evaporation, and anywhere over the land surface where there's available moisture to evaporate, there'll be greater evaporation there as well. And also, the water holding capacity of the atmosphere increases as the atmosphere becomes warmer. And those two things together mean that there will be more available moisture in the atmosphere. And that's going to do a couple of things. One is that atmospheric moisture is itself a potent greenhouse gas, so there will be a positive feedback to enhance surface warming. Of course, clouds play a complicated role in the climate system. Depending upon the type of clouds, there can be either a slight cooling or warming effect from the clouds, but the moisture vapor itself is a greenhouse gas that will enhance warming. The other thing, when you've got more available moisture up there, when you have storm events, there will be greater intensity of rainfall. Now, the frequency of rainfall might decrease. You put those two things together, and you have a potential for both more flooding events, particularly flash flooding events, especially in semi-arid places like this, and a longer dry spells, increased droughts. Now, one of the biggest sources of uncertainty has to do with what's going to happen to future emissions. We can't predict very well the future course of population growth, technology, and policy. And so we have to look at different scenarios about how that might change over the future. And I'm going to pull out, as others have done, 3 of these scenarios for later use in some of the graphics. The A2 scenario is we call the pessimistic scenario. It's the business as usual, continued rapid population growth, heavy reliance on fossil fuels, and so forth. The A1B is a more balanced scenario where you've got a mix of fossil and non-fossil fuel sources moving into the future. Also, a very wealthy populace, converging levels of standards of living, and so forth. The B1 is going to be the optimistic scenario where you have rapid transition to a non-fossil fuel energy base and transition perhaps to more service economy, that sort of thing. You can see, well, actually, even in the most optimistic scenario, there will continue to be warming, as others have noted. Okay, well, what are some of the things that we know almost for sure about how the water cycle will change and what will happen to water resources? Well, at the global level, we know that that precipitation will increase globally, about 1 to 2% per degree Celsius warming. But that doesn't mean that it's going to rain more everywhere and at all seasons. That's something that's very important to keep in mind. Just because there's a global increase in average precipitation doesn't mean that your neck of the woods is going to get wetter. We also know, as Professor Wagner had pointed, that the snow season is going to get shorter, and that's going to cause the stream flow to peak earlier. Any place that now is fed by snow, by the snow cycle. Glaciers are going to continue receding, and we've seen some dramatic pictures about that. In the near term, that will tend to support summer stream flows, because as the glacier gradually recedes, it'll release more water into the stream. Over the long term, once you lose that source, the summer stream flows will continue to decline. Sea level rise is inevitable, and that's going to lead to saltwater intrusion anywhere where you're relying upon a coastal aquifer. Also coastal flooding. We saw some great pictures of parts of Florida disappearing. That's off in the future, quite some distance, I believe. But meanwhile, there's already saltwater intrusion problems in many areas that are getting worse by the year. And more intense precipitation, which will have some important water quality impacts. When you get very heavy rainfall runoff events, you have a lot of sediment, dissolved solids, nutrients washing into watercourses, and you'll see spikes of very poor water quality. There's some water utilities here in the U.S. that are already grappling with the effects of heavy precipitation events. New York City doesn't have filtration on its water source, and it has seen some very heavy precipitation runoff events in recent years. I saw a picture of one of their reservoirs, the Sakari Reservoir. It looked like mud, actually brown, right after one of these heavy rainfall events, and then leads to subsequent algae blooms that are very difficult for them to deal with without having filtration on their system. But there are also some very big uncertainties, and as Professor Curry noted, the storm tracks are going to be, I don't want to walk away from the microphone, do I? Are going to be heavily influenced by things like the distribution of sea surface temperatures. And we can't, different models will, project those changes in slightly different ways. And so at this point, we can't tell exactly how the storm tracks are going to change in the future. And of course, that has huge implications for when and where it's going to rain, and therefore for what the water availability changes will look like in the future. There will be impacts, of course, on groundwater. The infiltration to groundwater depends upon the precipitation process, whether it comes as frequent light rainfall events or infrequent heavy rainfall events. And runoff variability, of course, is determined by the changes in precipitation patterns. Okay, we can try to look at some of these things using climate models. Now, one of the things that I want to point out here is that these are just 4 little snapshots, 4 climate models. They're some of the best climate models in the world, and the Canadian climate model and the Hadley model were the ones that Professor Wagner referred to, that predicted much wetter conditions in the western United States, and so those are the ones on the left-hand side there. One of the things that I want you to notice about this picture, okay, all of these models project an increase in global average precipitation, but the results of the model runs have been run through a large-scale hydrologic model. And here we're getting a prediction of the changes in average annual runoff, stream flow, from the different models. And that depends upon, not only how much does it rain, but how much does it evaporate over the land surface. And you can see that there are large areas in which some of these models predict very big decreases in average annual runoff. So the pinks and the reds, the red is 20 to 30% decline in average annual runoff. A few little pink spots, they're hard to see. That's more than 30% decline. I want you to note that the patterns are very different across these different climate models. And so, particularly for North America, there's in some instances a place that's predicted to get very wet, like the western U.S. in the Hadley or Canadian climate model. The other models don't show much change there at all. Other places are predicted to get quite a bit drier, but you can see there's a lot of variability across those different model results. Now, you might be inclined at this point to just throw up your hands and say, okay, these results are so different. How can the climate models tell us anything? Well, I wouldn't despair just yet, because if you start looking at a larger set of climate model results, some more consistent patterns do start to emerge. And this is some work done by Tom Wigley at NCAR. We tried to look at 17 different climate model simulations and tease out from that what he calls a signal-to-noise ratio. That's a measure of how well the climate models agree with one another on the direction of change, in this case in average annual precipitation. And everywhere that you see the oranges and the reds, the models are tending to agree that there will be more precipitation on average. So those high latitude areas. There are a few little blue spots, they're hard to see, but mostly in the subtropics. The models agree that it's going to get drier. It's likely to get drier in those areas. But you can also see an awful lot of green and yellow tones in which there's little agreement across the models. And that particularly shows up in the mid-latitudes. Europe and North America, that means that we're facing an especially uncertain future. And that means, and that's a reality. We have to deal with the fact that we can't accurately predict what's going to happen in this region. Okay, I think that Professor Washington showed this picture. This is another attempt to look at the results from many different climate models and get some insight as to how extreme climate events might change. This is an index of precipitation intensity, a very simple index, just the amount of rainfall per day for every day that it's a wet day. And you can see that in those same high latitude areas where the models tend to project higher average annual precipitation, they also project that when it rains, it's going to rain a whole lot harder. And you can see that over most of the globe, increased intensity of precipitation is projected, but less so when you get to the subtropics. Okay, the same technique was used to look at the length of dry spells. And here you can see that there's quite a bit of agreement for actually this whole Rocky Mountain region that dry spells may tend to be getting longer. And that means that we need to be concerned about how that might affect stream flow and water availability. So we again dug a little deeper and looked at an even larger set of climate model results. Here, Claudia Tibaldi and Linda Mearns, who are my group at NCAR, had a project where they took 20 different climate models. These are not the real high resolution regional climate models, but they're modern, fairly good resolution climate models. And they can look at different regions in North America and see how well the different models agree on important variables like temperature, precipitation at monthly timescales. And they weighted the different climate models by how well they reproduce the current climate. So for each variable, they provided a little bit more weight on the model that did a really good job of simulating that particular variable in the current climate. And so we looked at those two regions, what we called vaguely the Canadian Rockies and the U.S. Rockies. And one of the interesting things that we found is that the emission scenario really matters. It really matters a lot for the average annual temperatures that we're going to see. And I don't know if the green lines can show up very well, but the sort of light green line is the optimistic low emission scenario. And you can see that at the end of this century, the models are projecting warming of about 2 degrees Celsius, even in that low emission scenario. But if we're following a higher emission path, we can see a whole lot more warming than that. So let's just focus here on the right-hand side at the U.S. Rockies. We cut this up into two halves of the water year because I was interested in impacts on water resources. And so the top is the spring, summer, bottom is fall, winter. Fall, winter is actually probably more important in terms of water resources because that's when we get our snowpack accumulation that is important for later summer. But in the bottom right-hand panel there, fall, winter, under the high emission scenario, you're seeing, about a 4 degree Celsius average increase under high emissions. That can be held back to maybe 2 degrees Celsius increase if we follow the optimistic low emissions path. Now, what happens to precipitation? Well, there are some changes in precipitation, particularly in the Canadian part of the Rockies. And you see there's an increase, a general small but somewhat pronounced increase in projected precipitation. In the U.S. part, the projected increase in the winter is really quite small. I think that's less than 10%. In the summer, there's a small projected decrease. Now, those small changes can have big impacts on water availability. Here's some early what-if scenarios that were done. Just looking at, what if temperature increased by 2 or 4 degrees Celsius, and we, couple that with a couple of different possibilities for changes in precipitation. And here we're only looking at average annual runoff. And focus down there on the upper Colorado River, you can see that if we do see an average change in temperature of 4 degrees Celsius, you'd need nearly a 20% increase in precipitation in order to avoid a decline in runoff. Okay, and that's because with the higher temperatures, you're going to have more evaporation of the available water. So you're losing it that way. And that 20% increase didn't look all that likely in the previous graphs that I showed you. Well, now, if you want to really understand what's going to happen to the water resources of the western U.S., you need to understand that the mountains are where the action is. The mountains capture most of the available precipitation, and those are the headwaters for the rivers. The annual cycle of snowpack accumulation and melting drives the seasonal pattern of flow. Mike Dettinger at USGS and Dan Cahan and some of their colleagues, Iris Stewart, have done a lot of work looking at what kinds of changes will these western mountains likely see. And they've done some, just sensitivity analyses. For example, they've looked at trying to characterize the vulnerability of mountain snowpacks to something like a 3 degree Celsius temperature increase. And they looked at, where is the average temperature now just only slightly below freezing. And you can see a lot of the Cascades in Oregon and Washington and parts of the northern Rockies are particularly vulnerable to a winter temperature increase of only that amount. And so they came up with what's the expected fraction of annual precipitation with the temperature raised from now freezing, now below freezing to above freezing, and found that there's actually potentially large areas in which you would see those increases. Well, those changes are already happening. Again, Densher and Ira Stewart have looked at the changes in stream flow timing in the western United States. And that top left panel are the observed changes in stream flow timing over the period 1948 to 2002. And every place you see a dark red large circle, the peak of the center of mass, or the date on which half of the average annual stream flow has passed a gauging point, has moved earlier by at least 20 days. And you can see there are different levels, but there aren't very many places where the stream flow timing is getting later. Okay, and then they've looked at projections for the future under, in this case, a mid-range climate scenario, and found that there will be most places in the West seeing 35 or more days earlier in terms of the peak of the spring melt. Now, to keep all of that in perspective, you need to remember, as was pointed out to us earlier today, that natural variability is not going to go away. And I think water planners need to have a better understanding of the range of natural variability, because the standard practice in, let's say, the urban water utility industry has been to look at the period of stream flow gauge records, and assume that you could pick out the worst drought in that record and plan for that, and then you'd be safe. Well, if you look at these major western rivers, and here we've got an index on the top of the Sacramento River system in California. That's actually a 4-river index. And the Colorado River, you can see that there were long periods when conditions on both of those rivers are either much wetter or much drier than they've been in recent memory. Don't rely on what you remember in your own lifetime, and also don't rely on any recent trends that you've seen, because whatever we see is going to be some mix of natural variability and an underlying climate change. Okay, what if you want to go about assessing your vulnerability? So, for example, if you're a water manager, you want to assess the vulnerability of your system to climate change. Well, you can come at that a couple different ways. One way is that you can come at it top down. You can start with an emission scenario, work it through a climate model, work it through a hydrologic model, then through a model of your system, and look at your vulnerability that way. That's time-consuming and expensive. You can also come from the bottom up and start asking about, well, where are we vulnerable? Where are the potential problems that we might see? Is there a climate scenario that could make that worse? What would the impacts of that particular scenario be? Is that a realistic kind of scenario? This is the way the top-down modeling works. In the old days, of course, the climate models were very coarse resolution. Even now, though, at the current resolution, you have to do some downscaling in order to accurately capture the effects of mountain ranges on the distribution of precipitation and runoff. And then you can work those results through an integrated water resource assessment framework to understand how the changes in the inflows to the system will be affected by the way that the water is being used already within that watershed. The other way starts by focusing on the particular policy questions that we might be interested in. Can we preserve a particular fishery? This trout fishery, for example. Can we keep water temperatures cool enough to keep that fishery alive? What if we want to plan for acquiring new water sources? For example, a city looking to purchase water from an existing irrigation user. Look at what the thresholds, what the vulnerabilities of that choice might be, how it might be affected by either climatic extremes or prolonged trends. We did a little study for some urban water utilities. Actually, it was a cooperative project. We had these folks come in and talk about how they were viewing their options for assessing their vulnerability to climate change. And a lot of them really preferred taking the bottom-up look. They wanted to start with, well, what are some of the extreme events that we've experienced recently? How did they affect our utility? How might they affect some other utilities? And there were also some of the participants, Seattle and Portland in particular, who are already working with the climate impacts group at the University of Washington, using climate model results to assess changes in the annual hydrograph, changes in things like water temperatures that are very important for meeting their environmental stewardship responsibilities. And these folks came together and they shared their stories and they shared their perspectives. Some of the things that we looked at were glacier decline and loss of that as a source of supply. Calgary, British Columbia, Alberta came in and talked about the fact that they are losing their glaciers that feed the Bow River, on which they rely for supply, and talked about how they're planning to deal with that. Denver talked about droughts. We had some other drought case studies. Wildfires also have had a big impact on Denver recently. Miami was already dealing with saltwater intrusion and talked about the impacts that had on them. And here's a picture of the Bow River, the Bow Glacier that feeds the water supply for Calgary. Now, in most years, that contributes something like 7% of the summertime flow. But if you have a dry year, that is a major contributor to supporting the stream flow of the river that they rely on. They have very little artificial storage, no good places to put that, and so they can lose a large fraction of their summer flow once that glacier substantially declines. They're also dealing with really rapid population growth, about 3% a year in their service area. But they've got a lot of slop in their system because they've never had water meters. And so they have the luxury of being able to rely on demand management for a long time in the future. They found that when you put a water meter in, golly, people use 50% less water than they did before. It's just amazing. Now, droughts. We had a really bad drought in Colorado in 2002. And if you look at that tree ring record, the reconstructions, it was the worst drought, the worst single-year drought in about a 300-year record. And that was the first time since this Dillon Reservoir got constructed that it ever had lost water during the normal refill period, which is May and June. And so that's what it looked like in June 2002. And so that summer we were faced with severe outdoor watering restrictions. I think it was in Denver, it was once a week. Once a week for 15 minutes. You could keep your trees alive, but the grass, of course, went brown. But bluegrass is amazingly resilient. The next year it looked beautiful. So you can get by with a lot less outdoor water use than people might think. We also, that year, had the largest wildfire in Colorado history. It burned 138,000 acres, and it was almost strategically located to surround another of Denver's big reservoirs, the Cheeseman Reservoir, which is an important collection point, not only for water from the South Platte river system, which is on the, feeds the Colorado Front Range, but also they bring a lot of Denver's water over from across the Continental Divide, over from the Colorado river drainage through a couple of big tunnels. Roberts Tunnel feeds right into this Cheeseman Reservoir. Well, 2/3 of the area immediately above the reservoir got burned, and that soil there is very friable, and a lot of it washed off immediately into the reservoir, and so they had a big sediment loading event and big water quality problems that are continuing to this day. It's also very hard to reestablish vegetation on this stuff because it's like sand. Yes, you can put seeds on it, you can put burlap down, but nothing really sprouts and takes hold. So this is going to be a continuing problem for years to come. But the impacts of that event were actually dwarfed by the impacts of a much smaller fire 6 years earlier. Downstream of this big Cheeseman Reservoir, there's a little tiny reservoir that serves as the point at which the main filtration plant collects all the water and sends it on through to the Denver system. And that's the Strontius Springs Reservoir. And there was this little seemingly insignificant tributary immediately upstream of Strontius Springs, Buffalo Creek. And in that July, well, it's actually two months earlier, in I guess it was May 1996, a very, very intense fire burned right along that course of that creek and wiped out all the vegetation and baked the soil. It was just like putting it in a pottery kiln. It turned it into clay, impervious, and they had 2 months later a very heavy rainfall event, caused a flash flood, killed 2 people, and washed all of this gunk into the Strontius Springs Reservoir. Did $11 million of damage in a single day, and they didn't have any kind of monitoring system on that creek above the reservoir, so they didn't shut the works down in time and damaged some things pretty badly. Also lost 30 years of the useful life of that reservoir in a single day. And then later on, they kind of slapped themselves on the side of the head and said, why hadn't we managed the vegetation in that watershed ahead of time? It would have been an easy thing to do to thin the trees and prevent a fire of that intensity from burning. But, hindsight is great. This is why they came to our little conference, because they wanted to provide others with the benefit of their hindsight. That was a generous thing to do. Now, our options for dealing with the effects of climate change on water resource will be constrained by what we've already done with our water resources and how intensively we already use them. And you can see in the western U.S., we make intensive use of whatever available water there is. And some places, if you look at the lower Colorado, it looks like we actually consume more water than the basin produces, and that's because we get some from the upper Colorado. But we don't send much of anything through to Mexico. In a lot of these places, we use and reuse the water several times as it passes through the basin, so that by the time it gets to the end of the basin, it's not only laden with pollutants, but lots of people have a claim on it. Lots of people care about who's used it before them and how much is being used and how that use might change. If you look at the U.S. generally, I think there's something like 75,000 dams, over 50 feet high. So we've massively already modified our water resource systems, and we've used up most of the good dam sites, by the way. So that does limit our options for the future. And there's some new pressures on Western water resources. Rapid population growth. Southern California, I was told recently, is adding 300,000 people a year. And as more people move into Southern California, a lot of more people move out. It gets crowded there. And where are they moving? Well, they're moving here, and they're moving to the Front Range of Colorado and other places in the West. And so there's a lot of urban and suburban development, and those people are making new demands on water resources that were long ago already appropriated by other folks for irrigation use. And when these new people move in, they also want to use the water differently. They want to go whitewater rafting, and they care about aquatic ecosystems apart from just wanting to go out trout fishing. There are aesthetic values that they place on that. Then the federal and state governments put regulations on the streams trying to preserve things like quality and temperature so that those trout don't die out. Well, it's all well and good to say that we ought to plan for dealing with greater uncertainty, but Western water policy is kind of a messy business. In fact, there are lots of different people vying for the available water, and some of these value the water very differently or have very different needs. The fish, for example, need water every day. I think this cartoon originally came from a Bureau of Reclamation document that was looking at multiple purpose water projects and how you might balance the different demands of competing users. And that's actually a relatively simple situation because you've got a single decision maker ultimately who has to respond to those competing demands. But that's not the way that most water is allocated in the West. Most decisions are made by individuals, and some of them whom have rights that are different or better than other people's rights. We have a prior appropriation system which had good historical reasons for existing, but that gives some people a better claim on the water resource than others. So anyone who's got a junior water right or who relies on a direct stream flow, doesn't have a reservoir to draw upon, is really vulnerable to the changes in summer water availability. And that change in the seasonal timing with earlier spring melt, even if you get more precipitation on average, when it runs off earlier, you're likely to see declining summer flows, as the picture that you showed by Dentinger already showed. We're seeing in many places a declining availability in the high demand season. Anytime you want to make a change, and you're going to want to make changes because you've got these new urban water uses, you've got other things that you care about, and you might want to buy up some irrigation water rights and you move them to urban use. But anytime you make a change, you perturb that whole intricate net of interconnections among different water users. Okay, when you take water out of the stream and put it on a hay meadow in high mountains of Colorado, part of that water is consumed there in that hay meadow, but the rest of it percolates back to the stream eventually and makes it down to the next person to be used. Interesting kind of factoid, in Boulder, Colorado, where I live, when we had that severe drought, we were told, don't reuse your gray water. Don't take it out and water your plants. Why not? Because we owed our effluent to the next town downstream. So you flush your toilet and somebody owns it. Lovely thought, actually. But that's how interconnected the water resources in this environment of intense use and reuse are. And so when you make a change, when a farmer sells water to a city, you've got to keep those other water users whole. You have to offset any potential adverse impact that you might have on those other folks. Typically, you have to develop what they call an augmentation scheme, where you might release water from a reservoir someplace in order to keep the pattern of stream flow below your point of diversion the same as it would have been if you hadn't made the change. Well, calculating what might be an appropriate, an adequate augmentation plan in the future is going to be complicated, by the kinds of impacts that climate change will have on these systems. For example, if groundwater tables decline, a stream that you can now rely on to convey the water down to the next point of diversion, and maybe it's a gaining stream right now. The base flow is coming into the stream and keeping the water running down. If the groundwater table declines, it might become a losing stream. So you put a drop of water in at the top. Okay, I'm running out of time. And it'll sink down into the aquifer and disappear. So there are complications. It's risky for public agencies to talk about climate change. It's throwing one more monkey wrench into an already complicated situation. But there are some new developments in different places in the West that I think are moving in the right direction. They're articulating some principles and developing some processes that I think will become useful for planning in the future. There's a statewide water supply planning initiative in Colorado. They're bringing all of the competing interests in different basins together, getting them at the same table, talking about, gosh, how can we rationalize and coordinate the use of these systems, and they recognize that there are senior water rights. They have to be respected. The last bullet there, they want to foster common understanding of future water supplies. That caught my interest in particular because that provides an opportunity for the science community to engage with them and let them know about how climate change might affect their water availability. So if we're going to build that common understanding, we've got to discard the traditional assumption of climate stationarity. We can use some integrated models to simulate how these systems will change. And we want to embrace uncertainty. We want to use decision analysis methods to allow us to evaluate how can we best hedge our bets despite the uncertainty. Okay, we know that the changes are going to occur, new uncertainties, and there are some things that we can do to deal with that. Okay.